All right. So just a little bit of a, okay. So here's my talk, Beltrick Strikes Again. It's supposed to be about sunshades, coiling cables, magic tricks, turning things inside out, quaternions, the space of rotations of 3 space, and what it all has to do with the famous Beltrick. All right, so it all starts with sunshades, these sorts of sunshades. Come in pairs, put them into your windscreen, block the sun out. But interested in that, actually I'm interested in the way these things fold up. So they fold up kind of semi-automatically, so I'll twist in opposite directions here, and as I do this, they fold up really small, and they don't put much of a resistance here, put up much of a resistance here, they actually seem to be quite comfortable in this position, and you just throw them away like this. Now to really see what's going on here, I've cut out the core from one of these sunshades. I'm going to twist it again, so like this, and you can see some sort of saddle forming. So it's got 4 ears, and they start to overlap like this, and then they fold to each other. Now you've got 3 circles in your coil. Let's have a look at what's actually in the wrapper here. What's in the wrapper is a flat belt. It's a flat wire. It's a flat wire. So the wire's walls are perpendicular to the plane of the circle here. Perpendicular everywhere. And with this sort of wire, what it really doesn't like is being twisted like this on its length. But bending is quite comfortable. So when I twist like this, it tries to bend, but it tries to avoid twisting. And when I'm in this position, it's actually only bending and not twisting at all. And that's why it's so comfortable in this position. All right, so 3 coils, or 3 circles in this coil. What I can do is I can actually create a 5-circle coil, just to show you how that works. So we'll just pull until 2 of the circles are really small, like this. And then we do the same maneuver as before, and that folds up things into a 5 coil. You can actually do this with a finger the focus. So just put fingers into to separate the 5 circles in this coil. And again, the walls here, are all going to be perpendicular to the plane. So this sort of coil with the wall basically everywhere perpendicular to the circle of the coil, I call a flat coil. All right, now natural question to ask, is, can I actually turn this one here into a flat coil with just 2 circles or 4 or any even number of circles? Well, let's have a look. Do this. Can I do this? So this is 2 bits, and I can bend it together, but it doesn't really like being bent like this. Maybe not. It's actually the question that somebody else asked, these 2 guys here, and they asked and answered the question in this College Mathematics Journals article in 2009. It's actually a very nice article. They got the Article of the Year award, I think, for this article. So what they showed is that something like this, for example, can't be achieved by continuously deforming this one. Cannot be done. And same for 4 coils, 5 coils, 6 coils, 8 coils, and so on. And the proof is also quite pretty, and just makes use of some basic results from the theory of knots. Just to give you a flavor of what's happening, you have a ring like this. The ring has 2 boundary components, so there's 1 circle here, another circle there. They're separated as curves in space. If you fold up your wire in any way into a coil, you can look at these 2 boundary components together. They form a braid, like a closed braid like this. And you can use some basic results from the theory of braids, together with the linking number that goes with 2-component link, and then use some parity argument to figure out that these coils with even number of circles can't be created. Okay. When I first read about this, well, I had the feeling there should actually be a more natural way of looking at this. But I didn't follow it up, so I kind of forgot about it until Christmas. And at Christmas, I came across this Nature article, and in this article, there's some people talking about wires being bent in this strange way and used for all sorts of purposes. So, for example, here you see the wire in a tent or in a laundry basket, or here it's a ring, a paper ring, buckled in a certain way. So that kind of re-sparked my interest in this matter, and I started thinking about it and actually figured out what the right way is, I think. Okay, so to understand what's going on, let's have a look at rotations of free space. Okay, so every rotation, let's just fix the origin for all eternity here. So here's my origin coordinate system. And I need another frame later. So every rotation of free space is given by a rotation axis and an angle. Right? So for example here, we can give ourselves a rotation of free space always around the origin, which turns around this vector by this amount. All right? Okay, so that pins down rotation of free space. And we use this inside to model the entirety of all rotations into a model for the rotation of free space. And our model is just a solid ball of radius pi. So every point in this solid ball corresponds to a rotation. Corresponds in what way? Well, very easy. So the ball is centered at the origin. Take any point. The rotation this point corresponds to is given by this vector here going from the origin to the point. So that's the rotation axis. And the angle through which we rotate is given by the length of the vector. All right? Okay, so that's then quite clear what that point in the middle, the origin, corresponds to. That's just a trivial rotation. Nothing moves. Now, one special thing about this space or its model is that, well, if you move all the way out to the surface of the ball, then what does that correspond to? Rotation through pi. So it's a half turn. So just going up here accounts for half the rotations around this axis here. The other half is accounted for by vector pointing in the opposite direction. But this point here corresponds to a half turn. That one here also corresponds to a half turn around this axis. So they actually correspond to the same point. So what we have to do is, to finish the model, we actually have to identify opposite sides and typical points of the unit ball. That's what we're going to do. All right, and then this whole space, this model of the space of rotations, is basically like a Pac-Man space. Like Pac-Man runs around in this rectangle here and runs from left to right, but it doesn't bounce off walls when he reaches a wall. He just passes through and re-enters on the other side. Similar sort of thing here. If Pac-Man runs out to the surface of it doesn't bounce back. It just kind of goes straight through and re-enters on the other side, because those points up here correspond to points down there. Same thing. Okay, so they're closed in on itself. All right. Now this seems like a pretty straightforward space, except for the identifying antipodal points bit. It's just a basic ball, so it should be not that different from a ball, but it actually has some properties that are fairly different from the ball itself. So one property which will become very interesting for us is that if you have a curve like in a solid ball, like a loop, you can kind of just squish it together into a point, kind of continuously deform it into a point. Now this is not possible for some loops in this space. For some it is, for some it isn't. I just want to show you one loop that can't be contracted to a point continuously without breaking it or doing anything to it. And it's this one here. So we're kind of looking at the sphere or the ball from the side. We've got the south pole and the north pole. And we're starting here at the origin. That corresponds to basically no rotation whatsoever, right? No rotation around anything. Now we're going up here. Going up here. The points up here correspond to rotations around the z-axis. So all these points, they correspond to all rotations through angles from 0 to pi. So that's just all of those guys. So all of these rotations, they all correspond to individual points here, and then the rest correspond to these points here. So these are just all the rotations around the z-axis. So once around corresponds to this path. And it's really a loop because antipivotal points have been identified, so these correspond to the same point. I'll just claim this for the moment. That's it. So that's like one quite surprising thing. So the ball itself, everything can be contracted. Here's an example of something that can't be contracted. Now, the second surprise about the space is that if you kind of go for the same trip here, but now you kind of double up your trip, so you go twice around. If you go twice around, you actually get a loop that contracts. And I can show you how it contracts. So here we go. Back here. Alright, so this is a continuous loop. So for example, if you start from here, red point, we go up there to the yellow point, which is the same as here. So this is actually, there's no breaking here, so it's just kind of going like this. And then from here we go back to here. So if you just travel on this loop, we're just kind of going over and over, so twice around. You can see when I push this back together, it actually turns into the double loop that we started with. And now I can take this and push it further and further out, and it amounts to continuous deformation of this loop. And as you can see, the path, the loop contracts to a point corresponding to those two antipivotal points. All right, so that's something to keep in mind. Right? So we've got the rotational space. Every rotation corresponds to a point in our model, which is just the solid ball with antipivotal points identified. And there's certain loops in this space that contract, and the one to keep in mind is just the south-north loop, and there's certain ones that do contract. The one to keep in mind is that double south-north loop. Okay, now back to the wires. So what I want to see is that I can't turn this one here into a coil with an even number of circles. And what I want to do is actually I want to consider a class of wires, loopy wires, that's a bit more general than what I've got here. So I'll consider wires that can pass through themselves. So if you want to model something like this, like a real wire, we would be talking about embeddings of annuli into R3. What I want to consider is immersions. Okay, so I want to consider immersions that can pass through themselves. And what I want to show is that if I've got any two, like if I've got a coil made from viscose material that has an even number of circles and one that has an odd number of circles, I can't possibly transform these two into each other. Okay? And when I'm finished with showing this, what I've also shown is, of course, that the same is true for metal wires. You cannot coil this one up in an even way because it's odd, even. So if I could, then All right. So let's talk about ghost wires. All right. Here's a coil with two circles, and what I do is I squish it down, and now it self-intersects. Basically, I squish it down into the plane, and I kind of go around like this. So I've turned it into a double coil, which just goes twice around this ring. It's a little bit like going twice around our loop just a second ago. Okay, so what you can see here is I could arrange my two coil in any way in space, and by the same maneuver I could turn any two coil into the twice around. And what that means, of course, if I've got two coils, I can transform them into each other. Right? So say I've got one two coil, another two coil, I can transform this into that, I can transform this into that. So via here I can transform them into each other. Same sort of argument works for any even number of circles in a coil. So for example, if I've got a 10 coil, I can also do this, squish it down, go like this. I've got a 10 around. So all coils with 10 circles are deformable into each other. So all 2 coils are deformable into each other, all 10 coils, all 14 coils are deformable into each other. And of course the same sort of thing is true for odd numbers of circles in a coil. Alright. Now let's remember our maneuver from the very beginning. So this one maneuver here, this maneuver is really we're making up a connection between all the 1 coils and all the 3 coils. And as I said, all the 3 coils are deformable into each other, but now it also means that all the 3 coils are deformable into any of the 1 coils. Repeating the maneuver, I get a connection to the 5 coils, into the 7 coils, and so on. So what that shows is, overall, if I take any coil, say a 7 coil, it's an odd number, and a 83 coil, which is also an odd number, then I can deform them into each other. That's what I've just shown you. Okay? And the same sort of thing is true for any 2 even number circle coils. All right? So anything on this side transforms into each other, anything on that side transforms into each other. Okay? So what I want to show now is that taking any 2, like an odd one and an even one, you can't transform them into each other. And for that, of course, what's sufficient to do is just show that any representative from here, some representative from here, cannot be transformed into a representative from here. Right? So if I show that these 2 don't transform into each other, then I've shown a more general result that no 2 transform into each other. Okay, and that's now really, really easy with our setup from before. So what we'll do is we'll look at our once around. So there's an equator here, and what we'll do is we'll frame it, not for murder, but for loops. So we've got an equator here. Pointing along the equator is a tangent. So we'll have this point, this green vector point in the direction of the tangent vector. Then we've got the blue vector still tangential to the ring, to the wire. And then we've got one more vector sticking out. That's the red vector, is just a cross product to normalize and get an orthonormal frame of unit vectors. And you do the same for every point here. So as you move the frame around, it changes position continuously, but actually what you see is the blue vector is always sticking up. Okay, and now of course every one of those frames in space corresponds to a rotation of space. Right? So if we just take this guy for example, I can translate it back to the origin, and then there's one rotation of space that just does this. Right? Line them up. So every one of my frames in my framing corresponds to a point in SO3 in the space of rotations, and well, they describe a loop. Which loop is it? Well, as we go around, we basically turn this frame once around, so 360 degrees, and that means the loop that corresponds to this equator is just the south-north loop that we've had before. And of course, if we go around this equator here, we go twice around, right? Okay. So we've got a framing here, a framing there. If I was able to transform this guy here into that guy, let's start going like this, and well, the framing also changes continuously with me changing this position of the wire continuously, and as I change this continuously, the corresponding loop in our space changes continuously. So if I could change this into that would imply that I could change this one here continuously into that loop over there. But that's obviously not the case, because one contracts, the other one doesn't contract. If I could transform this one into that one, either both would contract or both wouldn't contract. So that's a proof, and it's a pretty natural way of thinking about the fact that sunshades don't coil evenly. Alright, so this was the first part of the talk. The second part of the talk is to tell you a little bit about what all this has to do with the belt trick. So I've got an ordinary belt, but for a bit more style I'll use a black belt, or for a bit more visibility I actually use a brown belt. So here we go. So what I'll do is I'll pin one end of the belt down to the ground, and I take this end and put 4 twists in. 1, 2, 3, 4. 4 twists. Okay, now the important bit is that I've just used this top here to impart a twist to the belt. Now what I want to do from now on is basically fix the position of this top bit, not rotate or twist it anymore, and only use the rest of the belt, move the rest of the belt, and get this twisting out. And it's quite easy to do, so let's just go for it. Like that. So it's gone. Right? I didn't do anything to this. The overall position stays the same. I maybe translated around a little bit, but that doesn't matter. But I can get rid of the twisting by just manipulating the rest of the belt. What does this show? Or what is it supposed to show? Well, what it shows is, again, that the south-north loop in our space of rotations collapses to a point. How does it show that? Well, I'll show you. Okay, so here we've got our twisted belt, and here we've got the end position. And now we'll also frame this twisted belt. So what we'll do this time is we'll take a frame and have it move up the middle line of the belt, so up the middle line of the belt. And we have one being tangential, which is going to be the blue one, and one being tangential to the surface of the belt, and then the other one cross product again. And as it moves up, you can see it kind of goes around like this. Actually goes around twice, right? Because we twist 4 times, we're actually going to rotate a total of 2 times, 360 degrees. And well, these frames again correspond to the 2 times the round guard. So the 2 times the round guard. Alright, and now it's also a closed loop because the frames that attach here and there are basically the same thing. Okay, now we do our belt trick. As we perform the belt trick, the position of this guy stays fixed, which means that at all stages of the belt trick, we're actually dealing up here with a closed loop. Okay, so the belt trick translates into a continuous transformation of this loop here into whatever that corresponds to. What does that correspond to? Well, we've got a frame attached to this, and it's just the same frame all the way up. It actually is just the identity. Right? So the belt trick shows that this guy here can be contracted to a point. That's what it does. Okay, so that's why people are excited about it. Apart from that, it looks pretty good. All right. Now, what does this have to do with our coils, with our sunshades? Okay, so let's do this again. So again, I give it 1 twist, give it 2 twists, 3 twists, 4 twists. But now I perform the belt trick in a slightly different way. It amounts to exactly the same thing as what we did before. Main thing is we keep the top bit, the orientation of the top bit fixed, and just manipulate the rest of the belt. Okay? So what I'll do is I'll first turn the twists into coils. I'm going to do this again. Okay, anti-clockwise. 1, 2, 3, 4. So twist into coils. 1, 2. Okay, so now all the twist is gone, and what's left is coils. Okay, now what I'll also do is I'll pass this bit here under. This doesn't change anything about the orientation of this part of the belt, right? It's still coils. And now I'll just pull, and that's the belt trick again, just a different version of the belt trick. Okay, so let's have a close look at what I just did. Okay. So here we've got the belt. The belt corresponds to this 2 times around south-north loop. Now we start changing things. Okay, start changing things from here to there. What do we actually get here? Well, when we think about it, these are coils, right? So coils, actually 2 coils. We've had that before. What that here really corresponds to is a loop that goes from east to west twice around. Nothing else. So the magic of the bell trick actually hasn't happened yet at this stage. I've kind of just turned the pictures here around. Okay, then I pass this end under. Well, at this stage, it's still basically the coil that we have. There's nothing essential that has happened here. So it's still basically twice east-west loop. Okay, and now you pull, and that's when the magic happens. That's when the magic happens. That's, if you now really look closely, that's when you see how the loop contracts to a point. Over here. Okay, so what that shows then is, well, if you take this part here and just bend the 2 bits together, what you actually get here is a 3 coil. Right? Now the magic happens when you do this. Right? So the magic happens when you do this. So the magic happens when you have the 3 coil and let go. So that's the magic. So what that shows is that the bell trick or the sunshade twisting maneuver is actually just another incarnation of the bell trick. So pretty neat. Okay, there's something else in here which is quite neat. So, I mean, I look at this maneuver, this twisting maneuver, and I can see, I can see exactly what's happening, but I still don't really understand it. So why is it 3? So why is it 3? Can I see this? Now, if I look at this picture here, I can actually see much better how I get these 3 coils. So let's have a look at this. So if you just go from here, what you do is you do 1 coil, and then you kind of do a reverse coil over here, and they cancel out. That's basically what happens in the bell trick. So I can go like this, and then I do a reverse coil like that, and I tie the 2 ends together, and now I've got a 3 coil, and now I just do the letting go, and that turns it into the ordinary bell. And also shows you how you can make coils with a lot more circles. So it's 1. Wait, I'll do this like this. 1. So that would be 3 coil. Go around again. 5 coil. Go around again. 7 coil. So 7 coil. And we tie ends together. So that's 7 coil now, flat. And we let go. And it becomes flat. So that's good inside. There's one more thing. Just kind of going back a couple of years, I met some guy at a conference, technician. He worked for a rock band at some point in time, and he told me that the only thing that you need to be able to do as a roadie is to coil cables properly. And coiling cables properly is definitely not what we do. What most people do is just kind of winding things around like this. So this is actually really bad for the cables, because what it does is it imparts a lot of twist on the cables, and for really thin cables, that destroys them. Right? So there's basically twist outside, inside, so it's just bad for the cables. So what you're actually supposed to do is exactly what I just showed you in terms of bells. So you're supposed to kind of go once like this, once like that, once like this, once like that, once like this, once like that. And if you can do this, you get a job as a roadie. If you can't do this, you can forget about it. Also, if you actually coil your cables like this and just throw them out like this, they go down completely flat, which is also a good thing. So I actually learned how to do this now, and I do this all the time. Oh, one more thing. You can actually perform a nice magic trick with this. So let's go around once, go around twice, 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 go around once, go around twice. All right. Now, this is a magic trick, but it can also count as an accident. So what might happen is, when you've rolled up your cable, like according to Rowley's rule, one of the ends might slip through like this. And let's just see what happens. Do this. So if you actually do this, you get a lot of knots. So it's just nice if you want it as an effect, but usually it's not nice if you try to uncoil a cable and you've got lots of knots all of a sudden. Alright, so that was the magic. Okay, so we had 2 parts so far. The first part I showed you that a natural way of seeing that wires like this only fold oddly, not evenly, ever. The second part I showed you what it all had to do with the belt trick. And now, I just looked at belt trick and everything I could find. And there were a few things that were kind of strange, and I tried to make sense of them. And I thought it might actually be nice to talk about this at this stage. So, to probably just look at this lady doing her dance. Let's look, let's just go back to the lady doing her dance. Lady doing dance. Oh yeah, here. So somehow this movement that she's making here, this dance, is also supposed to be the belt trick. Sometimes called the defiant belt trick. So I thought, well, it would probably be interesting for you to find out why this is also the belt trick. Okay. So let's go back to the ordinary belt trick. So basically start with this guy here and translate it into a loop in the space of rotations. It's just a 2 times south-north loop. And then we look at instances of this loop as we perform the belt trick. Every instance corresponds to a closed loop in the space of rotations. And you end up with a single point. So the path that we started out with has contracted to a point. So the belt trick again shows that there's loops, or that this particular loop, this double south-north loop, contracts to a point in the space of rotations. Pretty neat. Now there's a different way of looking at this whole setup, kind of an orthogonal view of looking at this whole setup, which also shows the same thing. So what we'll do this time is, instead of looking at the individual instances of the belt, what we'll do is we look at, we've still got this framing happening, in an individual frame. So for example, this frame here, what does it do? Right, so here it starts out somewhere, then it gets twisted 360 degrees, and then nothing happens for a while, and then we end up here. So the total effect is we've gone through the usual thing again. We've done this. So just looking at the path of this frame here up here, it will correspond to our usual guy. Well, we can look at the frame slightly below it. That will also perform a loop. So basically, in the space over here, you get a loop corresponding to the second frame, and that will be a slightly deformed thing. So the different frames here, or the journeys of these different frames, then correspond to a family of loops in here. So basically deformations of this 2 times south-north loop. And of course, eventually, we get to the loop that corresponds just to this frame down here. But this frame down here doesn't move at all. It's just this point again. So if you follow the progress kind of this way instead of that way, you've got a different way of seeing the belt trick doing what it does. But also, when you look at it this way, you actually get an explanation for why this is also the belt trick. Because instead of looking at the belt, kind of doing 2 times twisting and then untwisting, you just replace the belt by your arm, and the fixed bit here is your shoulder, and the moving bit is one way you put the plate and go like this. So you kind of do a 360 degrees, and it's all twisted up, and then you do another 360 degrees, and it's all out again. So that's also pretty neat. And now, this was supposed to be a talk for physicists, so there's a nice movie.
The great physicist Paul Adrian Dirac devised a topological trick with strings in order to illustrate graphically an elusive property of the spin of the electron. In quantum mechanics, all particles are connected to each other and to every observer in the universe. For an electron, there is a quantum state or wave function relative to a given observer. If this observer should walk around the electron, making a full turn of 360 degrees, then the wave function changes sign. This means that while a quantum mechanical system involving electrons is not brought back into exact coincidence with itself after it is rotated by 360 degrees, it is brought back into coincidence with itself after it is rotated by 720 degrees. Here is Dirac's visual metaphor, performed as the Philippine one.
All right. Now this is, I mean, in essence, all I wanted to talk about. Now, I've tried to express myself as simply as possible, but I've glossed over quite a few things. So if you want to talk about all this stuff in a very concise way, you're probably using the language of algebraic topology. We're talking about fundamental groups of things and covering spaces and things like this. So just to give you an idea of what I gloss over here, when I talk about these paths, I talk about them as if they were subsets of space, but really you have to think of them as journeys. So journeys. So for example, a continuous map from the circle to the space. That would one of those things, and not the image of one of those. Because the image can be really wild. Right? So the image, for example, has these space-filling curves, curves that really fill a solid piece of space. All bad, but can be made sense of when you just look at it in the right way. And now the last thing I wanted to do is talk a little bit about why this guy doesn't contract. So I've given basically explanations for everything else here. I've shown you how the double one contracts now in 500 different ways, but this one here, it just stands there as something that I claim is the case. And I had like two ways of showing this prepared, one a pedestrian way, one a quaternion way. And well, let's just do the pedestrian way first. So why does this one not contract? Okay, so remember, all this is happening, this transformation, this deformation is happening in a solid ball. It's a solid ball. And here was basically the distinguished disk we had, in which I, for example, contracted a 2 times loop. I'll just do it again. Here, kind of viewed it from the side. So, contracts to a point like that. Okay. And now we're interested in this guy here, this guy. So, the first thing you have to know about this sort of stuff is that if there's a way to contract this guy to a point, then there's actually also a way to contract it completely restricted to this disk. Why is this so? Well, I mean, if you think of this contracting wildly or kind of moving wildly around the unit ball, giving one of those deformations into a point, what you can think of is basically squishing everything that you see down into this disk here, and that's possible. Right? So, I mean, things might split up over these antipodal points, but since they're kind of symmetrical across, you can just squeeze things down and it won't matter. So, what I want to show, or give you an argument for, is that this guy cannot possibly contract inside this disk with points, of course, around here. Antipodal. All right. So first, what we'll do is we'll have another look at this instant of our double path. But this time, we'll just think of this region here, this region in between the 2 green lines, as a neighborhood. As a neighborhood, kind of a thickened up blue curve. Okay? And if we just take this out, what do we get? Well, we basically get a strip here, and the endpoints of the strip are somehow identified together. And they're identified by a twist. So what do we get here? We get a Möbius strip. It's a Möbius strip. Möbius strip has just one boundary component. Right? So one boundary component. So this is one continuous loop. Pretty obvious. Okay, so now the idea is, the pedestrian idea is that if I transform this loop any way I want, I can always look at this kind of thickened up neighborhood. And since I start out with a Möbius strip neighborhood, with just one boundary component, I should at all instances have just one boundary component of this neighborhood. However, when you think about it, eventually this blue loop is supposed to kind of come down to a point. And when you look at the neighborhood of this one point, it actually has two boundary components. So that can't happen. You can't continuously deform something with one boundary component into something that has two boundary components. So that was the pedestrian way. All right. Let's just see whether we can do the quaternion way too. So quaternion goes up here. So for the quaternions, the first thing I have to tell you is something about this contracting loops business. So here I've got a nice space and I contract the curve to a point. Now whenever that is possible, so whenever a curve contracts to a point, what I can also do is I can find another family of curves that contracts to this point, for example, on the original curve, and contracts in such a way that all intermediate curves also pass through this point. Let's show you quickly how that works. So starting with the same position, we now want to contract to this point. So what we'll do is we contract exactly in the same way as before, but we also do a little bit of a detour here, just going along the path to the green point and back again, and then continuing as before. So that gives us a loop that goes to the green point. And we just keep on going like this. So in all instances, the loops that we're seeing here pass through the green point. Eventually, we've just kind of got a connection between the green point and the red point, and then going back and forth between those two, and we can just kind of contract these into the green point. It just goes away. And we found a contraction. So, what this means is, for our situation here, is that if you go, if you can find a contraction of this loop into a point, then you can find one into this particular one, into the north-south pole, which means that we can actually assume that throughout the contraction, the loop always passes through this point. So for example, with the 2 times around, here's an example. So here's the 2 times around, and here's a deformation of the 2 times around that actually passes through this point. Okay? Yeah. Of course, so if it was possible to deform this one into a point, we would be able to deform it into the north-south pole and have all intermediate loops go through the north-south pole point. Okay, for that we need quaternions. And actually I just found out something today about quaternions. It turns out that the iPad thinks about rotations as quaternions. Didn't know that. The person who told me about this is Richard Koch. Anybody know about him? Well, he's the one who wrote Tech Shop. Just really nice to talk about this. Okay, so quaternions. What are quaternions? Well, you've got the real numbers, and doubling up the real numbers gives you complex numbers, and doubling up the complex numbers again gives you the quaternions. So they all look like this. You can add them, you can also multiply them, formally at least, two expressions like this, not a big deal, but you have to make sense eventually of product like I times I, which actually stays -1, j times j also stays -1. So all possible combinations, all 9 possible combinations of I with j with k, whatever, and these are the famous rules for making sense of quaternion multiplication. It goes back to famous physicist Hamilton. Okay, so with this multiplication, the quaternions turn into a field. So it's just as nice as the real numbers and complex numbers. Just something goes missing, which is the multiplication is no longer cumulative. All right. Now, it turns out that every rotation of rotations of the plane, the complex plane, are just described by unit length complex numbers, right? Similarly, you can actually describe all rotations of force space via these quaternions, but what's interesting for us is we can restrict things and actually describe all rotations of 3 space with quaternions of unit length. Alright, so let's just describe what happens to a vector when you unleash a quaternion on it. So this is a vector here, I component j and k, and actually you see the I, j, and k that you're familiar with, they actually come from quaternions. Alright, so this is a vector on the one hand, but it also can be interpreted as a quaternion, as the real part missing. Okay? So that's what we're going to do when we're rotating this vector as a quaternion. Then we've got the quaternion. We've also got the conjugate of a quaternion. It's defined pretty much exactly the way conjugates of complex numbers are defined. And then when we unleash q on the vector, we just do a multiplication inside the quaternions, q times v times conjugate q, and this puts the vector somewhere. Where does it put the vector? Well, that's what this guy says. The rotation that's affected by this is given by the axis q2, q3, q4. It's kind of the imaginary part of the quaternion. And the real part here corresponds to the angle around which you turn, which is the cos of the angle divided by 2. Alright. So every rotation of 3 space corresponds to a quaternion. Actually, it corresponds to 2 quaternions. Now, if you look at the unit length quaternion, what are they? Inside R4, they're just the unit sphere. Right? So it's kind of the surface of the 3-dimensional unit ball. It's a 3-dimensional manifold. So it's this guy here. Right? And typical points, it turns out, affect the same rotation. So Q and minus Q, they do exactly the same thing. So they rotate in exactly the same way, stand for the same rotation. So that makes this guy a double cover of the space of rotations of 3 space. Something very, very pretty. All right. Now we can actually pretty much see at a glance why this guy doesn't contract. Okay, let's do it. So let's ask our iPad, what does this rotation stand for? Well, it tells us one of 2 possibilities, right? So there's 2 quaternions that correspond to this. It tells us one, right? And then we go up, and continuously our iPad tells us corresponds to this. And so what it does, it traces a curve on the 3 sphere that goes from whatever that was initially to the antipodal point. Okay? But now we vary this curve in here, always keeping it to pass through these 2 points. Okay. Now as we do this, the path up here also goes around, but always connects those 2 antipodal points. Now they are really different here. Here they're the same, here they're different. They're always the same. So can it now happen that we contract to a point? Well, if we contract it to a point, that would mean basically 2 points, but not connected by anything. But obviously, throughout the whole movement, we don't get any rips happening, nothing else happening. This thing always has to stay connected by something that corresponds to rotations that are not just corresponding to 1 point. So this cannot be contracted because these 2 ends always stay separate. It's kind of a one class thing. Right, and over here, just for completeness sake, I've shown how this thing collapses, and let's just do this as the last bit. So here collapses down to a point. All right. Okay, and that was pretty much it. Just a couple more nice things to check out. So there's a lot of really nice animations of all this on the web. So for example, here's a computer program that does the bell trick and associates it with paths in the quaternions. There's a Australian science fiction writer, Greg Egan, who's written up some really nice applets to illustrate both the bell trick and just rotations of 3 space. And there's Bob Pelley having a whole page, a really long page dedicated to illustrating the Belgic. So all things to check out. And, well, I think that's pretty much all I wanted to say. Part 1, Part 2, Part 3, odds, and the end.